Okay, let's get started. Thank you everyone for joining this, our latest edition of our global webinar series. And in this edition, we'll be discussing the top capacitor myths that some of our FAEs, our field application engineers, deal with on a regular basis. So my name is Wilmer Companioni, and with us today is LeAnna Weakley. LeAnna, would you care to introduce yourself here very briefly?
Sure. My name is LeAnna Weakley. I'm a field application engineer with KEMET. I've been here about 3 years. I'm based in the Detroit area, BSEE from the University of Kentucky. So yes, I like basketball. And you can reach me at my email there.
Excellent. And then we have Andrew Mikulski. Andrew, you're up.
Thank you everyone for joining. My name is Andrew Mikulski. I am also a field application engineer with KEMET based out of Florida. I've been with KEMET for just over 3 years. I also graduated with a BSE from Northeastern University. And you can reach me as well at myname@kemet.com with any questions you have.
Okay. And as I mentioned earlier, my name is Wilmer Companioni, and even though I have a BSW just like LeAnna and Andrew, I am part of the marketing team at KEMET, and I've been with KEMET for the last 6 years. So let's get started with some of our top capacitor myths. The agenda we'll be discussing today these are some of the top myths that Andrew and LeAnna have seen on a pretty regular basis in the field. First off is this notion that I can always make my MLCC smaller as long as my rated cap and volt are the same. Then this idea that tantalum polymer is a no-brainer drop-in replacement for MnO2. You can easily switch from one to the other. And so thirdly, all manufacturers define life the same way. That this idea that the way that life calculations are done for electrolytic capacitors is pretty much independent of manufacturer. And then finally, the notion that safety caps, EMI safety caps and pulse caps are interchangeable. After all, a cap is a cap. So we'll get into that and what's going on there. So first off, the idea that I can always make my MLCCs smaller if my rated capacitance and rated voltage are the same. And this comes from the fact that, as we all know, electronics are continuing to miniaturize, and the density of electronics is increasing. So that drives this sense that, well, everything can just go smaller and you'll be all right. So take it away, guys. What do you guys think? What's the driving force behind this, and why this is a myth?
Well, there's definitely a big trend in the market. You know, everybody wants a smaller product that does more. So there is a big trend for downsizing products if you can. But you can run into issues with this, Wilmer, if you click to the next, especially with class 2 or class 3 type capacitors. This doesn't pertain to class 1s because there is no DC bias effect for them. But for class 2 and 3 capacitors, there is a DC bias effect. And this will change with package size. So the DC bias effect, what is it? You have all these dipoles within your ceramic material, which is a barium titanate for class 2s. And all the dipoles are within these domains, and you can see that on the picture on the right. So as you add a voltage, Wilmer, if you would, you can see here, as you add a DC voltage across your capacitor, all of those domains will start to line up with that voltage. And as it lines up, it leaves, I guess, Wilmer, you've used the word capacitate. I liked that a lot. It leaves less dipoles to to go towards your capacitance. They kind of get locked into that voltage there. And you kind of saw that red dot drop on the left as you put more DC voltage across your part, and you get less capacitance. Now, as you go down in case size, your layers of ceramic material get thinner, which means they're able to handle less of this voltage across them, and those dipoles line up a little bit quicker.
Okay. So, and LeAnna, you mentioned that that there's an effect from case size due to this. Can you talk us through a little bit of the magnitude of it and what it all means?
So I think one thing that's really interesting that we offer is our KSIM tool, which is a great way to look at capacitor performance. And if you have not looked at it, it's a great tool to have. It's something that's very unique. And one thing that we have is the ability to look at the DC bias effect on capacitors. So here you have 3 different capacitors, all have the same rating. So they are all 2.2 mic, 10 volt X7Rs with a 10% tolerance. And you can see here the significant difference in terms of the DC bias effect. That solid yellow line is a 0603 variant of that capacitor. And at the point that Wilmer has highlighted, which is about 3.1 volts, that capacitor loses about 34% of its total capacitance. Now, if you start increasing the case size, you increase up to a 0805, for example, that equivalent voltage only equates to a 2.5% capacitance loss, which is a significant improvement on the 0603. Now, if you go up even higher to a 1206, you lose even less capacitance. That delta is only about 1.4% capacitance loss. So this just goes to show that while the trend is downsizing, where everyone wants to get more out of smaller capacitors, there are design considerations that need to be taken into account for your class 2 dielectrics, your X7Rs, your X5Rs, that does not allow it to be an automatic drop-in equivalent.
So Andrew, what's causing that that exacerbated DC bias effect as you shrink case sizes?
So essentially it's the idea that, as LeAnna mentioned, that your effect on the dipoles is changing. And when you go to a smaller case size, you're essentially creating increased stress on the dielectric layers in that they're not able to, again, to borrow a phrase, capacitate as effectively. So therefore, you're not able to align your dipoles most effectively. So that's why with those smaller case sizes, your stress is increased, your dipoles are not able to align as effectively, and therefore you're not able to capacitate as effectively and get as high of a capacitance as you will with your larger case size MLCCs.
Keep using that term, man. It's going to be a thing.
It'll stick.
Okay. So next up is the notion that that polymer, speaking specifically to tantalum polymer capacitors, that it is an easy sort of no-brainer drop-in replacement for the MnO2 variant of tantalum capacitor. So once again, can you guys give us a sense of where this came from? What's some of the driving factor behind this, and why this is not necessarily true?
Yeah, so the tantalum polymers are similarly designed as the MnO2s. The biggest difference is the introduction of a polymer cathode. And one of the things that this does is it lowers your ESR. So your ESR is lower, which allows for greater ripple current capabilities. And that kind of draws from here is that the polymers are more intrinsically conductive than their MnO2 equivalents. Now, while that's a huge benefit, being able to have lower ESR and higher ripple capabilities, The problem becomes is if you drop it into a circuit that is tailored to a specific MnO2 part, for example, that has a higher ESR, now you're talking about the overall current draws and other performances within that circuit changing. And we've actually seen instances where engineers love the polymers and they want to design it in, but because it has that lower ESR, now they have to actually add resistance to their circuit in order for the performance current draws, for example, are staying equivalent. So while it is an advantageous part to use, there are some design factors that need to be taken into account when trying to drop it into your system. And one of those is that lower ESR having effect on the overall circuit design.
Okay. And as I understand it, besides just the lower ESR, which, as you said, if you aren't specifically tuned to have a low ESR, then that may not be that advantageous to it. There's also the idea of leakage, right?
Yes.
That's correct. Leakage is a big one. So in this slide, you can see that R6, that would be the leakage resistance. So with the MnO2 traditional type tantalum capacitors, here it's a 2.1 mega ohm resistor. So that's pretty high, which means your leakage current could be fairly small. Now, if we look at a polymer, you'll see that that resistance has gone down to 212.8 kilo ohms. So your leakage will actually be higher with a polymer. So if you need this part in an application where higher leakage would not be advantageous, you might not be able to switch over from the tantalum MnO2 over to a polymer type capacitor.
So then it would appear, though, as the leakage current of a polymer capacitor is about an order of magnitude higher than an MnO2 equivalent, right?
That is correct.
So then what are maybe some of those applications or some of those types of systems where you wouldn't want an MnO2 capacitor? I suppose something that's attached directly to like a battery and a rechargeable mobile device, right?
Right, battery lines, you definitely don't want high leakage on those types of applications. So if you were using something like an MnO2 with a little bit lower leakage, going up in leakage might not be something that you can do.
Okay, so then I guess to summarize this a little bit, when taking into account, trying to switch from an MnO2 to a polymer, you have to take into account the changes due to leakage and the changes due to that much lower ESR, right?
That's right. I mean, polymer is a great alternative to MnO2. There's no burning like there was with the traditional tantalum MnO2s. You know, the ESR is lower, which is usually a good thing, but if you're looking to drop and replace them in your existing circuits, you definitely need to take these things into account and make sure that it will work for you.
Okay. Thank you, guys. Andrew, any last comments on polymer to MnO2 replacements?
Yeah, as LeAnna mentioned, there are a lot of benefits that can come from switching from MnO2 to polymer, but just like we mentioned with the ceramic capacitors, there are additional design considerations that need to be taken into account in order to successfully design it in. And you can't just say that it is a drop-in replacement and your system will work perfectly.
Okay.
Just saw a question pop up. I just want to clarify that we're talking about tantalum polymer capacitors versus traditional tantalum MnO2 capacitors. So the cathode material on these parts is a polymer, whereas in traditional tantalum, the cathode material is manganese dioxide. So that's the two technologies that we are comparing here.
All right. Cool. Thanks, LeAnna. Next up is this notion, or maybe this misconception out there, that all manufacturers of aluminum electrolytic capacitors define life in the same way. And you know, where does this come from? Have you guys actually seen this in the field?
Yeah, actually, I've seen it, and it becomes a challenge when trying to compare between manufacturers. And there are a couple different ways that aluminum electrolytic manufacturers define end of life. The first one being catastrophic failure. So those are the very obvious failures, you know, parts break, things like that. The second one is a mechanical failure. So that is when the safety vent will open, and that can be done through various different mistakes, such as wrong polarity, excessive ripple, operating above rated temp, things like that. The biggest difference that exists between manufacturers is what they consider end of life in terms of parametric failures. So these are failures that you see through normal wear and operating. So this can be things like capacitance change, ESR, impedance, and leakage current. Now, while manufacturers look at these the same way, the difference is in the parameters that are actually looked at. So the biggest one is usually ESR. So we define our end of life as ESR being triple the quote unquote limit. Now, if you look at other manufacturers, they might say 4 times, they might say 2, they might say different numbers. So the idea is that you don't want to just look at life as a parameter. You don't want to just see the life number and say one part is better than the other. The emphasis should be on looking at what the parameters themselves are. That what is the ESR limit? What is their maximum? What is the impedance limit? So while there are some calculations that go into it, which LeAnna will talk about, there should be some observation on the actual parameters that are being looked at. It's kind of similar to the discussion that was made several weeks ago about our inductor technology, for example.
Yep. Just to clarify one thing, in this case, I want to once again say that when in this part of the conversation, we're talking about aluminum electrolytic capacitors. The lifetime of aluminum electrolytic capacitors is generally one of those parameters that people look at very clearly when selecting different capacitors. So speaking of how different manufacturers and people calculate life, what are some of the things that we do or that we have available to calculate life?
Right, so we actually have an online tool at elc.kemet.com, stands for Electrolytic Life Calculator. And you can kind of see a snip of that here. You can enter, your operating temperature, voltage, etc., and see what the lifetime would be of those parts. And these are part specific, not family. So you can actually see where your specific part would fall within lifetime. And this is all based on the Arrhenius equations, as you can kind of see up above, how we do calculate that lifetime of the parts.
Right, so with this calculator, instead of actually going through all the hand calculations and math yourself, which you're more than welcome to, you can just enter your specific operating parameters and for your application, and then get an estimate of life that way. Much quicker than having to dig through data sheets and do math and spot ESR and sum up the power losses. This tool will do all that for you. Andrew, do you have anything to add to this?
Yeah, the Electrolytic Life Calculator tool is a great tool. It's in the same vein as the KSIM. It's something that's very unique to us. And I think that it's a great way when selecting parts and trying to compare parts, it's a great way to make sure that you're actually using your operating parameters to get an accurate estimation of life, as opposed to just looking at the life parameter itself and going off of that. So it's a great tool. It's a great design tool, and it's something that we highly recommend engineers using to help them select parts.
Okay, excellent. So let's get to our last myth or misconception, if you will. This idea that safety caps and pulse caps are interchangeable. So LeAnna, I think you're going to take us through this one. Well, what do we mean when we're talking about safety caps, and why are they not interchangeable with pulse caps?
Well, this is actually something I see quite a bit. Pulse caps are a bit smaller than safety caps, and we'll talk about why. But I see a lot of my customers, or have seen some of my customers, using pulse caps in a safety capacitor application. And a lot of times that does not turn out too well. Safety caps are for either for your AC applications, either X or Y, line to line or line to ground. They filter out noise, differential for X caps, common mode noise for Y caps. And they are specified to these different, oh my goodness, I lost the word. Help me out here, Wilmer.
Noise sources, topologies, where are you?
Sure. But they do have all these qualifications, the ENEC, IEC, as you can see here, UL. They do have to be made in a certain way. They are called safety capacitors for a reason. So X capacitors actually will prevent a fire. So if an X cap were to fail short, there could be a fire occur, and these are specifically designed to keep that from happening. Now with a Y cap, if that were to fail short, somebody could get an electric shock. So these are specifically designed for safety to keep anyone from being harmed. So that's why they have to go through all these qualifications and things. That's also another reason that they're a little bit bigger than their pulse capacitors, the pulse capacitors that you see, because those are meant to be used in a different part of your circuit where somebody, there's not as much risk as like electric shock or fire hazard as on your AC lines.
And as you mentioned, besides just the qualifications, they're actually manufactured differently, right? It's not like you just took a regular capacitor and put it through additional testing and screening, right?
That is correct. They are definitely manufactured differently. The metallization on them is a bit different, and Andrew will walk you a little bit through an example on why the metallization is important within these capacitors. The potting materials, sometimes safety caps will have more, which is why they're bigger, because they're supposed to, protect against that fire and electric shock and things like that. So there are a lot of differences between pulse caps and safety caps.
Okay. So, and as you mentioned, LeAnna, these are manufactured differently. And Andrew, take us through this very scary looking picture you have here.
Yeah, so this is actually an example of a pulse capacitor that was installed to behave as a safety capacitor. Now, to explain kind of the difference is both capacitors are designed to deal with quote unquote pulse currents. The safety capacitors are connected to the main AC mains. They protect the supply from unwanted pulse currents, but they see constant AC and filter out occasional spikes. Now you compare that to a pulse capacitor, which is connected to pulse DC and prevents unwanted transient. It sees constantly pulse voltages and filters out the extremities. So In the pulse capacitors, the metallization is thicker than the safety cap. So what happens is that the self-healing capabilities are not as effective. So what you see here is that you have a capacitor that's trying to self-heal itself, and it is not capable of doing it. So then you have capacitor layers being damaged, which you can actually see there. And you cannot fix this. The capacitor is now ineffective. And that is why if you look at a pulse data sheet for a capacitor, we'll actually state that these should not be used in across the line application. So while the drive might be to use a smaller part, this can clearly show that if used ineffectively and not in the right type of application, the parts will actually fail and be damaged permanently. So if you are in a safety application, it is strongly recommended, encouraged, whatever you want to say, to use a safety specific capacitor, as they will not just heal themselves, they are designed for safety and for protection, as LeAnna mentioned.
Yeah, and you were commenting to me that you had a customer that that incurred quite an expense at replacing some of these manually after design process, right?
Yeah, these are not cheap. And as you can see there, when they installed these parts wrong, they got about 4% failure rate. So it might not seem a lot, but it is a significant number of capacitors. And as you mentioned, it's not just the financial expense, it is the time expense. There's a lot that goes into when you have these types of failures. So if you are in a safety application, downsizing and going to a smaller cap is not the solution to go. There's a reason that those capacitors are bigger.
It's not the place to cut corners, huh?
Exactly.
All right, thanks, Andrew. All right, so let's recap here really quickly. These 4 capacitor myths and sort of why they're there. So first one, as we were talking about, this idea that you can always make your MLCCs smaller as long as your rated cap and volt are the same. And this one is, obviously there's an exception there when you're talking about class ones. Class ones, because they don't have that VCC effect, you can definitely do that with class ones. But class twos, those thinner layers exacerbate that VCC effect. Secondly, the idea that polymer is a no-brainer drop-in replacement for MnO2. Yes, in many ways, polymer is a superior technology, but there are some key differences, as LeAnna and Andrew mentioned, that have to be taken into account. Key differences like the significantly lower ESR and your elevated leakage. Then the notion that all manufacturers define life the same way. This is patently false. All manufacturers have variances in their calculations. And furthermore, then it becomes a marketing game where some capacitor manufacturers try to make their capacitors look better by having favorable life conditions, if you will. And I think we have a couple questions to that, so we'll get to that point. And then finally, the notion that pulse caps and safety caps are interchangeable. Safety caps, true safety caps are rated as such because they've been manufactured and tested to meet fire prevention and safety standards. Pulse caps have not. So you can't make the replacement from one to the other and expect the same performance. So with that, I'll now open this up to our Q&A. And I already see that we have some questions that have been submitted through the Q&A window of the Zoom. If you haven't done so and you have a question, please go ahead and submit them now and we'll get to your questions. And then we'll try to answer as many questions as we can. And then if we adjourn and you still have some unanswered questions or follow-ups, please submit them through this link here on the screen, and we'll get to those at that time. So the first question that came in was one about, I believe it was when we were talking about downsizing MLCCs, that you need to verify the frequency performance, the self-resonant point. So that's a good point. That also moves as you shrink your capacitor. Even though you physically shrink it, but you still have the same cap value, your self-resonant point does move. And I guess I'll leave it up to LeAnna or Andrew, or even our bonus FAE Sam, if they want to get into a little more detail on that. So do you guys want to make any comments as to why that self-resonant point might move as you shrink? All right, I'll do it. One of the reasons it moves is because you have actually, you have less inductance, if you will. As you get smaller, you have less metal effects, less self-inductance, and that will cause your self-resonant point to actually move upward in frequency. So that's something to consider there as well. LeAnna, I think this one, or I think maybe it's Andrew. This one might be for you. The person asking this question, where we were talking about ESR as a definition of end of life, this person was under the impression that it was 3 times the original. Can you elaborate on that or have any comments to that?
Yeah, so if you look at our data sheets, they do define it as ESR times 3 times the ESR limit. And this is mainly due to the fact that ESRs can fluctuate when they first come off, when they get finished with manufacturing. And if you look at the data sheets themselves, and you pick the specific part number, these will actually have an ESR max. And that is what the end of life criteria is based off. That's why we say it's a limit. It's based off of that maximum, not necessarily the original value, because those original values will fluctuate. So even though that they will fluctuate, they will be very similar to that ESR maximum. So it still works effectively as a way to measure life.
Okay.
And that's just another example of how, the end of life is defined differently between different manufacturers. Some do define it as 3 times the original, whereas others have a limit, as we do. So that that just lets you know, you definitely need to check what the data sheets say before you compare end of life.
Yep. Another question here about X and Y caps. What does it mean when you're like X1, Y1, X2, Y2? That 1 and 2 and sometimes 3 designator, what does that mean?
Right, so that actually has to do with how they're tested, the peak voltage test. So I believe Y1s are tested at 8 kilovolts, whereas Y2s are 5 kilovolts. X1s, I believe, are 4 kilovolts, and X2 is lower than that. So Y1, has a double or reinforced insulation application. So that's for your really big safety concerns, then your Y2, that's lower voltage peaks. And then X's, of course, they're just for fire, right? Not for shock prevention. So they're tested even lower peak voltage testings. And that's what those mean. Gives you an example of how they're tested.
All right. So then I think this is the last question that came in. We have one about the trend of very thin polymer film capacitors. Like how thin are these getting, and have you guys seen any requests out in the field for film capacitors with very, very thin films, and maybe what are they used for?
Thin polymer film. When we say thin polymer film, that's kind of two different.
The thickness of the film, the thickness, like, sub-micron.
Okay. So just thinner film, not necessarily polymer, right?
Yeah, thinner film.
Okay.
I think by polymer they might mean polypropylene, that type of polymer, right? That's a polymer too.
Oh, okay. I don't know exactly what thicknesses are being requested, but that's something I can look at. Maybe Andrew couldn't speak to that more. But I know that the thickness of the film is being requested to be thinner a lot of times, again, because of size requirements, at least from what I've seen. I've had a few customers ask, well, can you do a thinner film and fit it into a smaller package for me? So I think that's a lot of what is driving thinner film. I think there are some other reasons as well, but I can't really speak to them, but we can definitely get back to you.
Okay.
Yeah. It kind of goes down with the whole, this trend for getting more in as small of a package as you can, things like that. And, we can talk, we'll get this more specifics to see where the trends are going. And we can share some feedback to whoever, the person who asked that question.
Okay. I think this might be one of the last ones we take. This one, maybe we need a little bit clarity, or maybe this makes sense to you guys. The question is there any back EMF? And if so, how to compensate for it? I think it might have to do with safety capacitors.
Can we get a little more clarification? I'm not sure what that.
Yeah, I think we need some more clarification on the source of the back EMF, or the potential source of this back EMF and what it might be. Or we can follow up with that later. All right, so let's get back to here. All right, so before we close out, let me remind you of some of our upcoming webinars. So these first 2 weeks in June, we took on some of the basics and even some of the not so basic concepts of capacitors. The second half of June, we'll actually start with inductors and magnetics and get into the similar flow. So on Monday, June 15th, we'll be talking about some inductor basics. Then we'll get into specifics of inductors and magnetics, going through power inductors and chokes. And we'll have a similar session toward the end of this month where we're talking about the common inductor misconceptions. And if you have any other capacitor misconceptions that you might want us to address and to tackle in future presentations, please make your thoughts clear in this survey, this post-webinar survey that you'll be receiving. And with that, I'd like to thank everybody for attending. Thank you, LeAnna, Andrew, and our sort of ghost FAE, Sam, waiting in the wings back there. Thank you guys for joining me in this presentation, and thank you everybody for attending. And we look forward to seeing you at another KEMET webinar. Thank you very much, and we'll see you next time.
Thank you all.
Thanks, everyone.